Jeff, we had the idea to have people rename themselves from the institution that they're coming from. So you know how to use the rename button.
Oh, I see. Okay. Rename.
Georgia, will you send Simon a quick email reminding him that we are expecting him to be getting ready to speak, since you already communicated with him?
Can you also add Andrei Lokov to a co-host? He's one of the co-organizers as well.
Hi, everyone.
Hey, Andrei.
Hello, Andre.
How are you?
Good, good. Welcome.
Thanks.
Thank you. So maybe we should talk contingency in case Simon doesn't show up. I don't want to lose any momentum. Any thoughts if there is a mistake on his end?
Yeah, I sent him an email, but he did respond to me today too about the recording. So I know
Yeah.
he's fine with it.
I assume he'll be here. Just he'll be a couple
Coming
minutes.
in the nick of time. Okay.
but I mean, you know, we have to wait a few minutes later if he's not here. There's not much we can do.
Okay. I'm gonna start the I think we should bring everyone in at 9:25, and we'll start with that. Oh, Simon's here.
Hi, Simon.
Hi, Matthew. How are you?
Yeah, okay, thanks. How are you?
Fine, thank you.
Good morning.
Morning, Simon.
Hi, how are you?
Shall we
So-
quickly check if you can share your slides?
Sure, let me do that immediately. Okay.
Okay, great.
So does it work?
Yeah, it seems to work to me.
That's great.
So I will probably share the entire screen because I also want to show some videos using VLC. So if I share only the PDF, it won't work.
Sure, sounds good.
Simon, this is Dan Spurn from the IMA. If you don't mind, can you jump out? Because I'm going to have a short introduction myself, and then I'll pass over to you.
Okay, sure.
Thank you so much.
You're welcome.
Sorry about that. My dog just decided to start barking. So I'm gonna should we let everyone in, and I'll share my screen.
Yeah, sounds good.
Okay, so are we running live now? I hope so. I want to welcome everyone to this first meeting, this first workshop for a program entitled Harnessing the Continuum, Partial Differential Equations, Calculus of Variations, and Machine Learning. And this first workshop is going to be focused on theory and algorithms and graph-based learning. And it'll be running for this week. And I want to, before we get further into how this workshop is going to run, I would like to acknowledge support from our corporate sponsors. The Mayo Clinic, the Cargill Corporation, and Target, who are generous in supporting this in this workshop. So the IMA is a place where mathematicians from academia, industry, and government share together and develop new mathematics to support those problems arising in these three different communities. We build and sustain research programs through training and thematic research programs, and we are experimenting now doing this online, and we will be interested to hear and learn about what is the best way to do this in this new world. We've been running these programs for a very long time, close to 36 years, and we've hosted over 20,000 on-site visits and have trained over 370 postdocs. So this program that we are kicking off today is in fact focused around two workshops. This first one running today is on theory and algorithms in graph-based learning. And there will be another workshop in November on optimal control, optimal transport, and data science. And so we look forward to invite you to come and participate in that workshop in November too. So we're very excited about that second program too. I would like to acknowledge support and ideas and hard work of our organizers coming from many different spots around our country. So thank you so much, Jeff, Eric, Brittany, Kojen, Adam, Dan, Rachel, Stefan, and Lexing. And in particular, for this workshop, I'd like to acknowledge Andrea Bertozzi, Jeff Calder, Andrei Lokov, and Matthew Thorpe for your hard work to get this workshop going online. So again, we are in a new world. I want to tell you a little bit about how we want to run this workshop. And we are a learning organization, so we will be trying to test things out. If things are not working well, we will try to change and update quickly. You'll be, as you know, sent out a single Zoom link. This will be in the seminar, or these talks will be in the meeting mode. We will also be simultaneously broadcasting on our YouTube channel at our homepage. All participants who come in will be muted with video off, but we like interaction, so please raise your hand and type in the chat box, and the chair of that meeting will be looking for that type of interaction, so it's not based just on the speaker. Co-hosts will unmute or ask questions as they come in. We do ask that you rename yourself to include your home institution. For instance, I've put the IMA next to my name. I think it helps drop some of those barriers that were experienced. After each talk, all participants will be sent to a single breakout room. There you'll have a chance to continue to interact with the speaker. And if you're not interested in continuing conversation, or if you're finished, you can leave the breakout room at any time. And to do so, you can either reopen your Zoom link, in which case you'll be sent to the waiting room before the next talk. Or if you return to the main room, we will then send you to the waiting room so that you're not waiting among all the other people. We do encourage you to build additional breakout rooms, and we can help you upon request. I do want to also note there's a poster session on Wednesday from 1:40 to 3 p.m. Central Time. It's on the website. Each poster presentation will be in a separate breakout room, and you will all participants will be given co-host privileges so that you can move between the breakout rooms. And we are happy to build additional breakout rooms to continue discussions. We do have room for additional posters, right? This is the great thing about Zoom, is that we are able to scale up. We have many posters, but we are interested in having even more of our community participate. We will also have additional information on the session soon. We're not quite sure whether we're going to be using the single link or a new link for this poster session. That will be probably given to you tomorrow morning. So please provide feedback so we can update and change if things are not working well. And here's some additional information: general questions with Georgia, IT questions with Chad. Well, financial questions are not really apropos at this time, but we do look forward to interactions. And thank you. I'm going to pass over now to Jeff, who will chair the morning session.
Okay, thanks for the introduction, Dan. So our first speaker this morning is Simon Masneau, who's from the University of Claude Bernard. So he's going to talk to us about self-avoiding approximate mean curvature flow. Okay, and we started about a couple of minutes late, so we'll go a couple extra minutes at the end.
Okay. Thanks a lot for the introduction. So let me share my screen. Okay, can you all see? Is there a way to, okay. So does everyone see my screen and the PDF? Yes?
Yes, we do. Yeah.
Okay. So thanks a lot for the invitation to speak remotely to this at this workshop. So I'm going to present a work which is, well, still a little bit an ongoing work with Elie Bretin from INSA Lyon and Xingkang Yuang from Claude Bernard Lyon University. So it's a self-avoiding approximation of the mean curvature flow, and I will actually tell you exactly what it is about later. So let me first give you a brief introduction. So there are many physical systems which involve interfaces which tend to minimize geometric energy, and there are many problems where this energy is either the area or an energy which involves the curvatures of interfaces under various constraints. We shall see some examples. So we are actually interested in the numerical simulation of such systems. So I know that the main focus of this workshop is about graph-based methods, and actually I'm essentially going to talk about a continuous method for the continuous approximation of continuous systems. However, as you we'll see later, I'm going to introduce a reaction term, which actually could be generalized to other situations, including situations where you have also a graph-based method in some situations, or also some situations where you work with the neural networks. I will give you at the very end an example where this term could be used as well. So what I'm going to say about a continuous perspective, it could be actually generalized to other perspectives, including discrete ones. Not all discrete ones, of course, but some of them. So examples of physical systems where a geometric energy is involved. There is, of course, the classical situation of the wetting of a droplet on a lotus leaf. And here the area which is minimized is the energy which is minimized is the area energy under some, of course, constraints, such as the fact that the droplet is lying on the leaf, the gravity, and so on. There are several parameters that have to be taken into account, but essentially the geometric energy is the area energy. Another well-known situation is the case of bubbles or sub-foam, where in this case you're minimizing a multi-phase area. And here what I mean by multi-phase is the fact that in each bubble there are different phases, one phase for each bubble. So that's why it's the multi-phase area, the area of the interfaces between all these phases. The 2D equivalents of minimal surfaces are the structures of Honeycomb. So it's the 2D multi-phase perimeter, which is minimized here. Another example of multi-phase energy, the well-known example of silicones. So it's a typical example of a polycrystalline material. And you actually have a multi-phase inhomogeneous area, inhomogeneous in the sense that it's a weighted sum of areas, and the weights are the so-called surface tensions, which are essentially due to the crystalline orientations of your grains. Another example, this has been, for example, the subject of collaboration with physicists working on nanomaterials. So the case of nanowires, where you're minimizing a multi-phase anisotropic area. So another example where you have a physical system involving the minimization of a geometric area. And now let's talk about higher order energies, and typically a second order energy like the Elfrich energy, which is given here, which is involved to explain the shape of a structure like this one, so a blood cell, the boundary of a blood cell. And so this is a typical example of a second order energy where you take into account the mean curvature of the interface, the Gaussian curvature of the interface, and there is a parameter here which is called the spontaneous curvature. And one underlying well-known geometric energy, so underlying in this global energy, is the so-called Wilmore energy, which is given here sometimes with this additional parameter, which actually incorporates topological information. So I'm going to talk a little bit about the Wilmore energy because it plays a role in the reaction term I'm going to introduce later. So I described so far physical systems where you have interfaces which minimize geometric energies, but you have also, many applications where you need to minimize such kind of energies. So this is an example from magnetic resonance imaging, where you are given a series of slices and you want to reconstruct a volume such that the slices of this volume coincide with, well, binary, so segmentation of these slices, and you want the global volume to have a smooth boundary. So typically what you minimize is, for instance, the Wilmore energy. So this is the reconstruction that we have here. So we start from binary versions of these 2D slices, and we are able to reconstruct a volume such that every 2D traces at the same height correspond to what you have here, and the boundary minimizes the Wilmore energy. So here is a typical situation. Okay, another situation which is less well, it's not real. I mean, it's purely artificial. So, but what I wanted to stress is the fact that the method we have proposed is also adapted to the situation where the slices are not parallel and not planar. So it's possible also in these cases to reconstruct a volume whose boundary minimizes the Wilmore energy, and such that the corresponding 2D slices do indeed coincide or approximate these slices here on the left. Okay, well-known example in image processing, the case of or discrete surface processing, the case of the smoothing of a digital shape using the Wilmore energy. So here again, it's the typical situation where you're not necessarily minimizing the energy, but you're flowing in the direction of a local minimizer. So it's typically the L2 flow with respect to the Wilmore energy. This is what we have here. Okay, so let me now try to explain the situation. So how to approximate the minimizers you're interested in. So typically what you can do is to pick a representation of the surface. So you have many possibilities and many situations. So you can either use a parametric continuous representation of a surface or a graph representation of the surface, either a graph representation of a surface or a volume representation, and the interface between the various nodes of your graphs do indeed correspond to the surface that you're interested in. You also have many methods involving the level set representation, and then all family of methods which are based on phase field approximation. I will, for those of you who never heard about phase field approximation, I will quickly recall what it is about. So once you have picked a representation of the surface, you can try to minimize your energy or an approximation of it. So typically, if you have a graph, you will use, well, you know, many methods for the minimization of energies defined on graph, typically the mean flow max cut method and so on. But you can also, concerning the level set methods or the phase field approximation, try to solve directly a static Euler equation associated to the energy that you want to minimize, or you can also try to solve the time-dependent Euler equation with the idea that after convergence of the time-dependent Euler equation, you will get the solution of the static Euler equation. So this talk focuses on phase field approximation and time-dependent Euler equations, but as I will explain later, there is space to generalize to other situations. And this talk is motivated by the following issue. Can we efficiently minimize while avoiding undesirable topology changes as the surface evolves? So there is a sort of contradiction here, because you all know that switching from parametric continuous surface to level set method was precisely motivated by the fact that you wanted to avoid to be stuck with topology changes, and you wanted to have very flexible method which is able to incorporate and pass through these singularities, and in order, for instance, to do a mean curvature flow without caring about singularities. This is true, and this is always true, but the point is that there are some situations, as I will show you later, where you really don't want to change the topology. I will give you example, but a very famous example is this one. Take the mean curvature flow of this dumbbell in 3D. So as you know, in finite time, there is creation of singularities and then convergence to two balls, and then these two balls will decrease to a point and then disappear. And the point is that there are some applications where you are interested in such kind of flow, but you don't want any creation of singularities, and you don't want the surface to be split in two parts, and you want to preserve the unity of the surface, and you want to, so I will show you other examples. So, and the other point is that, as you know, working with parametric continuous surfaces is nice if you don't want to have topology changes, but it also raises many numerical issues that you usually don't have with level set methods or phase field approximation. So the idea is to combine the interest of phase field approximation with the constraints of keeping the topology of your surface. Okay, so a brief survey on phase field approximation. So The basic idea is the following. You are interested in the approximation or in the minimization of the geometric energy defined on a surface. So what you will first do is to consider that this surface that you assume to be closed is the boundary of a set. And you look at the characteristic function of this set. So this is a singular function, 1 here, 0 outside. And you will replace the characteristic function, the binary characteristic function, by a smooth approximation, by a function u, epsilon, which is equal to 1 inside, 0 outside, and there is a transition zone, and the width of the transition zone is epsilon. So typically, if you compute the norm of the gradient, you will have that it's 0 inside and outside, and in the transition zone, it's essentially 1 over epsilon. So it does indeed concentrate on the transition zone. Okay, fine. So here, this set can be seen as an approximation of the boundary of your set E. And as you know, the area of the boundary is called the perimeter of E. Okay, so now let's do this simple computation. And this will explain, I hope, why, so this will motivate the van der Waals-Cagniliard energy, which is very famous in phase field approximation. So do the computation of this. You remember, as I told before, that the norm of the gradient of U epsilon is 0 inside and outside, and 1 over epsilon essentially in the green zone. So when you integrate the squared of the norm of the gradient times epsilon, what you get at the end is the area of the green zone here times 1 over epsilon. Okay, so this is essentially 1 over epsilon multiplied by epsilon times the perimeter of E, epsilon times the length or the area of the boundary. Okay, so this is essentially equivalent to the perimeter. So you can consider that this energy here, in some sense, is a good approximation of the perimeter of your original set E. The problem is that if you try to say, let us pick functions U epsilon which minimize this energy, what you will get is any constant function. Obviously, any constant function has 0 energy. So you want your minimizers to be binary functions so that they are close to the binary function which represents the characteristic function of E. Okay, so how to force that? This can be easily done using what is called a double well potential, typically this one. So it's this smooth function, one-dimensional function G, and then you look at this energy there. So the integral of 1 over epsilon G of U epsilon, and if you impose that you're constraining this term, then of course, as epsilon goes smaller and smaller, so once again, let me go back here. Since U epsilon is an approximation of the characteristic function, the approximation is better if epsilon is small. So what I would like to do is to have a smooth approximation, but also a nice approximation. So with epsilon quite smooth. And if I impose these constraints, the smoother is epsilon, the closer is U epsilon to a function which is either 0 or 1, so a characteristic function. And this motivates this energy here, where you recognize the epsilon times the norm of the gradient to the square. So the difference with the term I mentioned before is that there is a factor 2 here. But the reason is that when you minimize this energy, there is a balance between these two terms, and they will be essentially equal. So you will have 1/2 of the perimeter plus 1/2 of the perimeter. This is how the approximation works. So the so-called van der Waals-Cagniliard energy, so the phase field approximation of the perimeter, is this energy here. So once again, just to summarize, I have a characteristic function of a set. I'm approximating this characteristic function by a smooth function, and I will compute a smooth energy associated to the smooth function. And I'm saying that this smooth energy is an approximation of the area of the boundary of E. This can be justified rigorously. There is a famous result due to Modica Mortola in 1977, where they proved a result of gamma convergence of this p epsilon to an energy which is, so if U does indeed coincide to the characteristic function of a set E, the limit energy is indeed a constant parameter times the perimeter of E. And if not, if U is not this, then it's plus infinity. So, okay, and now why is it interesting to have, I won't enter into the details of what gamma convergence is. I guess that all of you know about it. So for those of you who don't, it's a very nice notion of convergence for functionals in a variational context. And why is it interesting to have this notion of gamma convergence in a variational context? Because it's interesting because there is a connection between gamma convergence and minimizers. It's written here. If you have a sequence of functionals, so here typically the p epsilon functionals, which are equicursive, so it's a compactness assumption which is satisfied in our case here, which is gamma converging to f. And if you pick for each fn a minimizer, un, then every cluster point of this sequence of minimizers is a minimizer of f, and the energy of U is the limits of the smooth energies of the smooth UN. So it's a notion of convergence, which is really well suited in an optimization framework, because it tells you that if you have a nice approximation of your limit singular energy, then minimizers of your nice approximation will be close to minimizers of the limit singular energy. So it's very useful. In connection, so let me explain you why I need this. Sorry for these tricky details, but it's quite easy to understand why it's used. So what is called the phase field optimal profile associated with E and the energy P of E is this function here. So this function involves three things: the sign distance function to E, the parameter epsilon, and an optimal profile, this which is given here, which is actually a minimizer of this energy. So what does it mean? Just in two words, it's just a definition of an approximation, which is nice because it's very economic. So it's the optimal 1D way to approximate across the boundary in an optimal way your characteristic function. So imagine that I have a characteristic function of a set. If I do a smooth approximation, I will have something which is smooth here. And if I take across the boundary, I want to be as economic as possible when I'm looking at the limit energy, which is the perimeter. So the best way actually to do the approximation is to consider this optimal profile. There are, of course, infinitely many ways to do a smooth approximation of your characteristic function. And the best smooth approximation is this one. It's the most economic in terms of the van der Waals-Candillard energy, which gamma converges to the limit singular energy. So what you get is that this phase field optimal profile do indeed converge to the limit characteristic function. And its smooth perimeter does indeed converge to what you're interested in. So a multiplicative constant, which is actually related to the definition of G, times the perimeter of E. Okay. Now, so the point is the following. I have a smooth energy, P epsilon, which is a smooth approximation of a singular energy, which is P of E. And I'm saying that minimizers of P epsilon are good approximations of minimizers of P of E. To compute these smooth minimizers, one way to do that is to compute the L2 gradient flow of the smooth energy, which is given here. And the thing, just to make the connection with what I said earlier about the Wilmore energy, the thing is that, as you might know, the gradient flow of the perimeter functional is the so-called mean curvature flow. And this quantity here, the L2 gradient of the smooth perimeter of U epsilon, actually approximates the mean curvature of your singular set, of the boundary of your singular set in the transition zone. This does tell you something very interesting, is that if you consider this energy here, which is the approximate perimeter plus this term here, this is an approximation of the mean curvature. And this energy here is a nice approximation of the combination of the perimeter plus the Wilmore energy. So in the smooth case. And so this has been studied by De Giorgi, Bellettini, Paolini, and more recently by Röger and Schätzler. And they proved actually a very nice gamma convergence result, which is quite difficult to prove. You need some tools from geometric measure theory, but it's very useful because what I know from now is that I have a smooth energy, which is a nice approximation of a very singular energy, which carries information about the area and second order information on the boundary. Okay, so again, if I use the nice approximation I mentioned before, I can say that this nice approximation does converge to the characteristic function of E. Its smooth perimeter does converge up to a constant to the perimeter, and its smooth Wilmore energy does converge up to a perimeter to the limit Wilmore energy of the boundary, if the limit boundary is C2. Otherwise, this quantity, of course, is not defined because the mean curvature is not defined otherwise. Okay. So why is it interesting to use this kind of phase field approximation? I will show you a numerical example where I'm simply considering this equation here. So you remember that this quantity is the L2 gradient flow of the approximate perimeter. So what I have here is an approximation of the mean curvature flow. It's really an approximation. And actually computing limit solutions of these, it's quite easy using Picard iterations for this map. And this can be done very easily with Fourier series and periodic boundary conditions. And the advantage of this method is that it guarantees you a very high spatial accuracy. So let me give you an example. So this is an example of a starting interface. I have an approximation, so 1 here, 0, and there is a very thin transition zone, so it's really a smooth approximation, and I'm applying exactly this time-dependent equation here, which is an approximation of the mean curvature flow. And you see that you get very nice approximation of the mean curvature flow for the starting surface. So it works pretty well. And it's very fast to compute using a Fourier series. It's not fine. So can this be extended to the case of the Wilmore functional? The answer is yes. So in this case, sorry, I just come back. In this case, if you compute the L2 gradient flow of this energy, you get this time-dependent system, and this can be discretized implicitly in time. And again, you can use Picard iteration for approximating a fixed point. You can implement it with Fourier series in space. You have stability conditions, but it works pretty well. So let me give you an example where I start from this shape and I'm involving and converging to what is called the Lawson-Kirshner surface of genus 4, which is a minimizer of genus 4 of the Wilmore functional. Okay. Now, so the key aspects of phase field approximation for area and Wilmore energies are the following. The basic idea, I would like to insist on that, is that you replace singular energies. Why singular energies? Because the perimeter of a set is really an information which is concentrated on the boundary, so it's very singular. So you replace singular energies with smooth energies. And if you have smooth energies, it's easy to deduce from these smooth energies smooth gradient flows. So what I say is that gamma convergence of the smooth energies can be proven for area and Wilmore. Smooth minimizers approximate sharp minimizers, so the minimizers of the limit singular energies, you can design very efficient numerical schemes. But of course, the natural question is the following. From these smooth energies, you can deduce smooth gradient flows. And what is the connection between the smooth gradient flows and the sharp flows? Do phase field flows approximate sharp flows? It's the case for the limit minimizers. It's not necessarily the case for local minimizers, but for the minimizers it's true. But what about the flows? So you can prove that it's rigorously true for area, and it's also true for Wilmore. There is a rather recent paper by Fei and Liu where they prove rigorously that there is convergence of the phase field Wilmore flow to the sharp Wilmore flow. So here is the definition of the Wilmore flow. As you can see, it's rather tricky. You have the surface Laplacian of the mean curvature, you have the second fundamental form, and you have a very singular term, which is the very nonlinear term, which is the mean curvature to the power 3. Okay, so the problem with this flow here is that actually it's fine as long as you don't have appearance of singularities, but the problem is that this approximation do create singularities which are not natural if you think about the Wilmore energy. So a typical example is this one. You start in 2D from two disks which are very close one from the other, and then you see that there is an 8 which is formed here, which goes on evolving. Same thing here with these 3 disks. So when you do the evolution with respect to the Wilmore flow, you get creation of singular structure, which is given here and which does evolve. So why is it a problem? You have the same in 3D. You take 2 closed cylinders and they will try to merge. And this is not natural if you think about the Wilmore function. There is no reason that they really merge, or at least let's rather say that the Wilmore flow is well defined until singularity may happen, and then you might have different possibilities. And the point is that this phase field approximation choose one possibility, which is not necessarily the best one. So another example of merging here, you see that there is a bridge which is created between the vertical and the horizontal cylinder, and another example here of a connection which is actually really related to what happens here. Okay. So why isn't it naturally related to the Wilmore flow? Because actually this configuration that you have here is of course singular, but it's not, it does have an infinite relaxed Wilmore energy. So you might have heard about the notion of relaxation. The idea of relaxation is that you extend the definition of a functional which is defined for smooth functions to unsmooth situations which are limits of smooth function. If you take, for example, these 2 sets with cusps here and there, actually the union of these 2 sets has a finite relaxed energy because you can approximate by a sequence of smooth sets with uniformly bounded Wilmore energy. So this is a nice singular situation. This is not a nice singular situation because there is a paper, well, there is a work by Bellettini, Dalmaso, and Paolini that tells you that in order for a set to have a finite relaxed energy, it must have a non-oriented tangent everywhere on the boundary, which is obviously not the case here. Here you have 2 crossing, well, 2 tangents actually. So there is not one and only one non-oriented tangent. Instead here, you have indeed an oriented tangent at the cusp point. Okay. So just a very quick digression. The fact that you get these solutions for the phase field approximation of the Wilmore flow is due to the fact that there are smooth solutions to the Allen-Cahn equation which have singular nodal sets. So these are well-known situations where these are, well, situations of smooth solutions whose 0 set has a singularity, like here. So these are very classical examples due to Dong, Fife, and Pelletier, and later Kowalczyk, Packer for the generalization to other situations than just one crossing. You might have actually many, many symmetries. Okay. So let me, how much time do I have? Not so much. So, later, after the introduction of this classical phase field approximation, there was a nice paper by Luca Mugnai, where he actually observed that in 2D, if you look at the second fundamental form, which carries the old second order information, you have that the mean curvature to the squared is actually equal to the norm of the second fundamental form to the squared. So he proposed to replace the classical phase field approximation for the Willmore functional by this quantity here. And you can observe that as epsilon goes to 0, this does indeed converge to a quantity which is supported on the boundary of your shape. So sorry, my former notation was E. Here it's denoted as omega, but it's the same idea, times the squared norm of the second fundamental form, which is in 2D exactly the mean curvature. So Mugnai's approximation of the Willmore functional is this one. And what you observe when you do the L2 gradient flow of that, and you try to see what happens for surfaces, is that indeed, I will skip the details, but when you compute the gradient flow and you compare with the original Willmore phase field flow, you have an additional reaction term, which is given here, which is very, well, which is very nasty, actually. It's this very nonlinear term. And I will skip the details, but the idea is that when you do the evolution with this model, then you observe that indeed there is no possible crossing. So all shapes remain at a certain distance one from the other. This can be seen in 2D. This can also be seen in 3D. You see that the two cylinders here are evolving by the Willmore flow as long as they are not close one from the other. And when they start to be close one to the other, they just deform. So they take into account each other. So let me stress the fact that the underlying evolving interface coincides with the Willmore flow as long as it is smooth. But in the case where it starts, so there is possibility that singularities may be created, then in that case, it starts to repulse. So there is a repulsion effect. So we try to look at that term and try to exploit it. So we observe that this very nasty term, which I gave here, which comes when you develop the L2 gradient flow of Mugnai's phase field approximation, this nasty term here can be actually rewritten this way, which is a little bit more tractable. And what you observe is that it's actually related to the distributional Jacobian. So in 2D, B of U is essentially this. So hey, you may, of course, wonder, what about using this term in all dimensions? So first, this is maybe not a good idea because if n, so n, what I will call n, u is my function, I'm considering the gradient, and then I'm considering the normalization of the gradient. So this is the actually the normal to each level sets of u. And so if n is regular enough, so just in W1 n minus 1 Sobolev space, then the distributional Jacobian of n is a weighted sum of Dirac masses. So it's not adapted for charging singular sets of n of dimension greater than 0. And I will explain you later why it's important to do that. So of course, but the point is that this distributional Jacobian is B of u in dimension 2, but not necessarily in higher dimension. So what can we say about B of u in higher dimension? And what happens if n is, or if n, so if u and thus n is less regular? Okay, so we perform some numerical simulation and we observe that B of u indeed in a higher dimension charges singular sets of n of dimension 0, but also sets of dimension strictly greater than 0. So this could be interesting. I will tell you why, but it's inconsistent. So it depends on the boundary configuration, on the regularization kernel, etc. So there is no robust way to say, okay, these kind of sets are charged, these sets are not. Okay, so the basic idea I would like to insist on that is that this reaction term does imply the first order derivative of n. Okay. So let us consider this parameter, this term that we'll call a jump term. So I take n sigma, which is a modification of my normals n. I take the gradient, I compute the product of the gradient with n, so this is a matrix, this is a vector, and then the scalar product with the vector. So it can be expanded this way. And what is interesting is that when n is smooth, the norm of n is equal to 1. So when you derive this equality, you get that this term is 0. So this tells you that essentially this term will not charge points where n is smooth. It will only focus on points where n is unsmooth. Why is it important to focus where n is not smooth? Let me skip that, because if I take a set E and I'm considering the set of points where n, so let us consider the skeleton of this set E. So the set of points where the distance function is not differentiable, which are also the set of points where n is singular. So at these points, I have what is called the skeleton. So the skeleton of this ring is this circle union these points. The skeleton of this band is this straight line. The skeleton of this rectangle is this and this. So this and this, okay? And you see that this is the typical points where when I start to apply a geometric flow, these are precisely the points where there might be contact. Okay, so what are we going to do? We're going to now to focus on this term. I'm maybe accelerating a little bit because I'm a bit late. So let us focus on this term, which is rather nice. I mean, I have a sign distance function. I take the gradient of this sign distance function, which is n. I take the gradient of n, okay, times n, and times n itself. So I have this term, which can be computed rather easily, and n must be convoluted first, just precisely first to avoid problems where it is not differentiable. Okay, so what we can prove is that in a certain, I will skip the details, but in the context of the space of functions with of special functions of bounded variation, we can prove indeed that this jump term, we'll call it this way, does indeed converge to something which is supported on the singular set of n. So in this case, I have indeed that Sn sigma will not charge anything except points which are along this singular set of n, okay? So we can observe that for spheres, we can observe that for circular tubes, and we actually, after a few numerical simulations, have a conjecture, which is so far is a conjecture, which is that we have a decomposition of this jump term into a weighted sum of random measures, which are supported on n-1 minus j dimensional sets, whose union are the discontinuity set of n, so of my normal field. So why is it interesting? Because as you can see here, my normal field has here a one-dimensional singular set and a zero-dimensional singular set. So I need to be able to charge both this one-dimensional singular set, the zero-dimensional singular set, and in higher dimension and codimension, higher dimensional singular sets. Okay, so so what we are going to do now is just to consider the approximate mean curvature flow that I showed you before and add a reaction term, which is derived exactly from this jump term. So this is the basic idea, and it's not necessary to enter more into the details. So I'm considering my approximate mean curvature flow and perturbating it with this jump term. What do I get? Without jump term, the mean curvature flow of the dumbbell just evolved like this. With jump term, I have something which does indeed preserve the topology. There is no splitting. Fine. Another example, if without jump term, this should disappear very quickly because I have a ring with small radius. So this should disappear quickly by the mean curvature flow. Instead, it does indeed, well, it is preserved. The topology is preserved. Okay. The case of a simple filament, if I apply a classical mean curvature flow to that, I have something which disappears very quickly, but instead it does nicely evolve. And here is another example here. So we believe that this is actually a mean curvature flow of codimension 2. Okay, let me show you a few videos. Okay, the evolution, first evolution, another one. What is interesting here is that you see the topology is absolutely not modified, but I can play with this because actually my reaction term reacts to singularities of order 1/epsilon. But here I have something which is 2/epsilon. So I can actually weight my reaction term in order to avoid, to allow one topology change, but not all topology change. This is done here. You see that, okay, you see the evolution here. The unity of the filament is preserved, but I'm able to let this inner rig disappear, but there is no breaking. Fine. Okay. So application to the Steiner problem, and I will conclude with these two applications. Steiner problem. How much time do you have? Do you have 2 minutes more?
About 3 minutes. That's good. Yeah.
3 minutes. Okay. Thanks a lot. 3 minutes should be enough. So first example, the Steiner problem. The Steiner problem, you are given a set of points and you want to find the shortest connected path which connects all points. Okay, you have many recent methods which have been proposed for the phase field approximation of this problem. It's very difficult to approximate this numerically. So I'm jumping into the details, but what I want to express is that thanks to this term, what we do is that we indeed able to apply the approximate mean curvature flow, phase field mean curvature flow, plus the reaction term, which avoids the degeneracy of the evolution. So this is the kind starting from these points and a cube which envelopes the points. We let, so we do a deflation of the cubes and it does converge to this, which is indeed a perfect candidate for a Steiner solution. Same thing here. And let me show you some example. Okay, this is the phase field approximation, which gives you in the limit a Steiner solution associated to this set of points. So essentially, I'm solving a codimension 2 problem. Okay, same thing here. Sorry. Okay, another example here. So it doesn't work. Why that? Okay. Here it is. So another example with 50 random points, and we are able to compute the Steiner set associated to these 50 random points. Okay, it works, and with no breaking, nothing. Same thing for the plateau problem, so the problem of minimal surfaces. So I will directly jump to the simulation here, where depending on the topology that you choose at the beginning, you will converge to different limit minimal surfaces, which are all valid valid minimal surfaces. Other examples, and let me show you. Okay, maybe this is a bit fast. Okay, another example. I'm almost done. This is also a bit fast, sorry. You see that it does indeed converge to a solution, and we're also able to obtain hybrid solutions between the plateau problem and the Steiner problem. So it's absolutely possible. And it's interesting because it's related to problems in geometric measure theory involving flat chains, actually. Okay, so let me conclude. I'm a little bit late, sorry. So let me conclude saying that we introduce a reaction term which promotes topology conservation for geometric flows of a surface in arbitrary dimension and codimension. So of course, this reaction term is introduced in the specific context of phase field approximation. But what you actually need essentially is to have a sign distance function to your surface. So this can be used if you have a volume graph method. This can be used for level set methods. And there is also a recent papers where neural networks have been used to estimate or to learn sign distance function for shape representation. There is, for example, this deep SDF method by Park et al. And other also more recent papers. And of course, it's easy to imagine that what we did, which depends on the sign distance function, can be indeed used to impose in a geometric flow a topology conservation. Thank you for your attention and sorry for being a little bit late.
Okay, thanks for the really fascinating talk. I have lots of questions, but let me first ask the audience if there are any questions for the speaker. There's a question, can we get the slides? Would it be okay to put the slides up on the
Sure.
IMA website? We can talk later. Okay.
Of course.
So I have some questions, but I'll just ask some now, and then we can maybe talk in the breakout room. So should I think of this term you've added, right? So obviously you're not getting mean curvature flow anymore, but should I think that it's like when you get to a certain spatial resolution, it treats it as like a one-dimensional problem now, and so you're doing this thing in codimension 2, but you can have a hybrid thing where some part of the surface is doing mean curvature motion, and like some part is doing motion.
One thing I should specify is that actually this term does not play any role if your interface is far from the skeleton. So it starts to activate when you close. So when you're far from so you see, take for example a ball. If you have a ball, your skeleton is just the center of the ball. If you are far from so if your radius is big enough, then this is really the mean curvature flow. There is no perturbation of the mean curvature flow. But this term starts to activate when you're close enough. And otherwise, what you have is actually that there is a sort of cutoff. So the cutoff makes the term invisible when you're far from the skeleton. So it's really an activation when you are close to the creation to the creation of a singularity. So I agree with you that when you see the approximate mean curvature flow with this reaction term, this additive reaction term, you might think that it's a totally perturbated mean curvature flow, but actually it's not. It's only perturbated when you are close to singularity creation.
I see. Interesting.
So we don't have a full characterization of these, but what we have is, formal asymptotics, where we observe that indeed, if the distance is big enough, it does not play any role. It's really zero. So.
Okay, I also had a question about the Wilmore part of the talk. So is there a notion of weak solution for the Wilmore flow that is unique, sort of beyond these singularities that form?
Sorry, say it again.
Is there a notion of weak solution to the Wilmore flow, like there is for curvature motion, that takes you sort of beyond the formation of singularities or topological changes?
It's an interesting question. So far, not really. So so of course, for the classical mean curvature flow, the extension is the Brachy, for instance, the Brachy flow, which is indeed adapted to going beyond singularities. But as you know, there is no uniqueness. So it will be the same for the Wilmore flow. There is no way, I guess, to guarantee the uniqueness of the extension. I'm not sure that that this has been characterized fully so far. I don't think so. So I mentioned the convergence of the phase field approximation of the Wilmore flow to the real Wilmore flow, but it's in the smooth case. If you want to extend to a Brachy definition of the it's not clear that it's. I haven't seen so far a clear extension. So there are things that have been done, but nothing which is indeed characterized as well as for the Brachy flow, for the mean curvature flow.
I see. So maybe if there aren't any other questions from the audience, maybe we'll move to the breakout room for a bit for further discussion.
Okay.
So thanks for the great talk.
Okay, thanks a lot.